John Sargrove and his marvelous E.C.M.E, which stands for Electronic Circuit Making Equipment. System made operational in 1947. The first audacious plan for highly automated production of low-cost radios to serve underdeveloped countries. A stillborn project, largely because of political changes abroad. Born in 1906 in London to Hungarian immigrant parents, his given name was John Adolf Szabady, and it was changed to John Sargrove in 1938. His parents brought him back to Budapest to receive his primary school education, but he returned to London in 1920, where he studied at the Polytechnic in Regent Street, now called the University of Westminster, while undertaking apprenticeships with several small engineering firms. He gained a great deal of practical design experience and landed a job as a patent researcher in 1930 with Tungsram Electric Lamps Limited, later organized into Tungsram Radio Works Limited. By 1933 he had become chief engineer and remained so until his departure in 1940. By the mid-1930s, Tungsram was on a quest to develop an all-stage valve for domestic receivers, usable as an RF or IF amplifier with variable mu, a superheterodyne mixer, rectifier, and also as a modest power amplifier. Tungsram, who began their business around 1904 in Hungary with the owning of the world's first patents for producing tungsten filament light bulbs, by World War I was also producing radio vacuum tubes in modest production quantities. The Hungarian market for light bulbs and radio tubes was too small to support an industry that could thrive only on high volume, with enough revenue that could finance continuing research, quality control, and manufacturing automation. So they never actually brought their all-stage vacuum tube to market in the 1930s. Because of protectionist policies in effect in various countries, they were compelled to set up manufacturing operations in other countries of Europe and the UK in order to expand, but apparently they did not generate as much income from licensing fees for product development as, for example, Philips was able to do. Sargrove, as a patent researcher, was certainly aware of this early 1930s innovation, the spray shield tube, as implemented by Rogers Radio Tube in Canada, a scheme in which an oxyacetylene torch atomized zinc wire stock into a molten spray applied to the sandblasted exterior of a glass envelope vacuum tube. These pictures from 1933 show how Rogers in Canada initially zinc-coated their tubes. The same technology is employed in the USA by Majestic and soon appears on valves made by Philips in Holland. For consistency of application, rather complex machines had to be designed that still required constant worker monitoring and loading and unloading of the tubes to be coated. More or less conventional carousel machines that could not be integrated into continuous processing lines. So Sargrove was clearly aware of this prior art to simplify manufacture of radio parts and finished products. The industry seemed to be confident that progress would continue to be incremental for many years to come. With the UK officially at war with Germany from September of 1939, we find him resigning his position with Tungsram in 1940. In the war years, he becomes chief engineer with Electrophysical Laboratories and with Mervyn Sound and Vision Limited, engaged with the development of photoelectric devices for military applications. Some of the work provided material for a number of papers appearing in professional journals, and the work produced patentable devices. Less well known were his contributions in research of electronic automation for the armaments industry, an almost perfect experience background for his audacious plans to streamline radio manufacturing on an unprecedented scale. He engaged in activities to demonstrate his high professional standards, not only by seeking membership in 4 professional institutes, but also to contribute fully to the various institute activities. In 1939, he joined the Institute of Radio and Electronics Engineers and eventually was elected Fellow of the institution. Throughout the rest of his life, he was a member and chairman of both the Program and Papers Committees and the Technical Committee, as well as various conference committees. He was also accepted as a member of the Institute of Electrical Engineers in 1942, becoming a Fellow in 1949. Finally, he gained membership of both the Institute of Mechanical Engineers and the Institute of Production Engineers. In 1944, Sargrove takes his success with applications of electronics to automation processes for a number of clients to form his own company, Sargrove Electronics Limited. As hostilities wound down, Sargrove was able to rekindle his desire to implement radio manufacturing automation on a scale never before attempted. With private backing, he formed a separate company, John Sargrove Limited, to develop the E.C.M.E manufacturing system, electronic circuit manufacturing equipment. His announcement of having placed the system in operation in 1946 generated enormous interest in technical circles, and earning him the first Clerk Maxwell Premium of the Institute of Radio and Electronic Engineers. The big idea: circuits to be fabricated by molding grooves and depressions on both sides of Bakelite phenolic resin plates less than 1/4 inch thick. The plates were sprayed with flame-vaporized metallic zinc and then face milled to cut away the excess zinc. The filled grooves then served as interconnect wiring, and spiral groove areas served as inductors or chokes. The recess area served as capacitors. Graphite paste could be sprayed through stencils to form resistors. The details shown in patent disclosures reveal a seemingly unprecedented level of thinking on how to implement his concept into actual product. Even in the initial filings, he was thinking of how this fabrication method could be employed in other electronic instruments such as a television or oscilloscope. Here what we see is a functional, handmade prototype used to pitch his idea of a very low-cost medium-wave receiver for developing markets in Africa, South Asia, and the Orient. This prototype did not make use of an all-stage valve. The prototype in a cabinet made of presumed Bakelite sheet stock. Front and backside views showing tuning and volume control knobs. Such a cabinet with so many sharp corners makes correcting blemishes more time-consuming. The final cabinet had much fewer restrictions for quick buffing. I think the grill would present even greater problems in cleanup after molding. Beginning at number 1, Here we see samples of the first actual Bakelite moldings serving as the base substrate for spray zinc coating. Number 2. The Bakelite is given a fine grit blasting on both sides to greatly enhance the bonding of the molten zinc aerosol. Number 3. The front and back sides are now fully coated with zinc, perhaps about 10 mils thick. Number 4. The panel goes through 2 or maybe 3 stages of face milling, coarse removal of the bulk zinc, and then finer cuts to produce a smooth zinc-free surface. Number 5. Note that capacitors of higher value with smaller surface area could be made by molding a thinner wall between the surfaces. They reasoned that these thinner features would need to have a domed profile to withstand ejection from the molding operation and for long-term temperature cycling in operation. Patent disclosures show the design concept using currently available valves shown in the prototype and does not show the tuner portion. I have not found a schematic of the production type A3 receiver using the UA55 special all-stage valve. While this quest began in 1937, the only actual embodiment of this concept for tungsten was in the UA55, released in 1947. It appears that Sargrove contracted with Tungsram in England to make this tube. On the right are the basic features of the design. 2 beam tetrodes using an ingenious mechanical arrangement for a common cathode. A 55-volt 100 milliampere filament allowing for a minimum configuration 2-valve set to be powered directly from a 110-volt mains. This valve can be configured to function as a mixer for superhets, or as a variable mu IF amplifier, or as a 1-watt audio amplifier, giving more than adequate volume for a small tabletop receiver. It was even stated that the tube was useful as a mains rectifier, with the benefit that the tube, otherwise rejected in manufacture, could still serve satisfactorily in that service. A very few examples of these valves do exist in tube historian collections. It is likely only a few hundred to a few thousand valves were ever manufactured for Sargrove. The audacious plan used sophisticated automation to manufacture highly integrated circuit panels requiring almost no human labor. Only a few dozen people to oversee the machinery. A possible increase in labor efficiency of 20 times. The feature article in the August 1948 issue of Fortune magazine headlines, "The new method, now to be described, is at present being successfully carried out and differs from these earlier methods in many respects. The most notable difference is that the insulating plate employed is not merely a supporting device. It is molded into such a structural form that, when fully processed, without manual aid, it contains the inductors, capacitors, resistors, potentiometers, tracks, switch, and other terminations, together with conductor paths, in an interrelated and interconnected manner." The machine consists of 2 lines, 25 meters long. The input side is shown of both lines. At the left side, blank boards are fed into the machine for the grit blasting, zinc spraying, face milling, and continuity testing. On the right side is spraying of resistors, testing values, varnishing boards, insertion of eyelets, and final testing. On the left side, stacks of bare Bakelite plates are loaded into a vertical conveyor track. The process begins with grit blasting. Plastic panels carrying the proper circuit channels and contours file into a grit blast chamber where their shiny surfaces are roughened. Photocells scrutinize the blasting job. The photocell at the left determines if surface was properly roughened. If not, grit blasting operation is halted. Circuit details show up clearly in the picture. Shallow round depressions in panel will become condensers. The circular grooves will form inductance coils. The entire panel surface on both sides receives a smooth coat of molten zinc. Spools of zinc wire, bottom of picture, feed 4 oscillating metallizing jets. Ethane, propane, oxygen, and compressed air also flow into the jets in precise sequence and volume. Diamond-tipped milling heads remove the metal everywhere except in the circuit channels and other specially sunken areas. Here panels move past the first of 3 banks of cutters, each taking a shallow cut. Deep cuts would generate enough heat to warp the panels. Tiny sockets needed to hold added components shoot down the inclined track originating at the top of the picture. The sockets pass in front of a photocell and are sidetracked if faulty. Sargrove is now at work on new techniques for building sockets in place. This is a view of the end of line number 1. This picture shows the simpler tuner panel. The more complex panel is transferred to line number 2 for spraying through stencils, graphite to form resistors, testing of circuits and component values, installation of valve sockets and other interconnect terminals, applying a varnish sealer, and final testing. Mr. Sargrove on the right showing the finished tuner panels as they exit the line number 1 machine. I do not recognize the other person. Electronic inspector tests finished circuits. I think the inspection module is part of line number 2. The Fortune magazine caption reads, E.C.M.E includes a high-speed electronic inspection device which makes 50 separate circuit tests in 20 seconds. If 2 faulty panels come through in succession, E.C.M.E is quickly shut down. After inspection, panels are varnished and baked. Installing the board stack into a cabinet was easy enough. At this point, it's obvious Sargrove had not spent any resources in production line final assembly of product, which would certainly have been easy enough to set up. How many were actually built? There appears to be no contemporaneous surviving record. I'm guessing probably 200 to 400 or less might have been completed for distribution to various sales agents and government entities for evaluation. How many survive? There are only 2 in England, 1 in Australia, and a reportedly excellent example was found in a curio shop in South Africa in 2017. There are claims that there was an effort to export them to Rhodesia, Tanganyika, and Kenya. Samples would have definitely been sent to India and mainland China. A single example of a Sargrove superheterodyne receiver exists in the British Science Museum, using 4 of the UA55 all-stage valves. This is a schematic of the superhet, showing how the all-stage UA55 valve could be used as a converter, oscillator, variable mu IF amplifier, detector, and audio amplifier, and half-wave mains rectifier. The following are the best views I could find of the finished versions of the basic two-valve Sargrove Type A3 receiver assembly. The tuner circuit board is the rear panel of this assembly. Therefore, you tune the receiver from the back side. This was not thought to be much of an inconvenience, since it was expected that there would be only one or two stations in range to listen to. I presume that the small black knob at the top center of this rear board is a compression capacitor for regeneration control and serves as the volume control. Note where graphite was sprayed through stencils to form resistors. Note also that this more complex board, serving as mount for the two 9-pin valves, put a greater premium on surface area available for the capacitors. The footprint for the capacitors was reduced by molding undulations that increased their surface area by maybe 20% without having to increase their overall diameter. I think that the bottom center control is the mains power switch. The radio required a long wire antenna. The tan-colored top center device is the other view of the compression capacitor used for regeneration control and therefore effective volume control. The UA55 valves plug directly into sockets inserted into the molding, i.e. there is not a separate tube socket assembly. Note, it is a local receiver for environments where there are few broadcast stations. No need for a calibrated tuning dial. Just turn the knob on the back until you hear a station. I have a 3-valve Tesla local receiver circa 1955 that has a tuning knob on the front of the radio. It also has no markings. You just tune until you hear something. In Czechoslovakia at that time, you were not likely to have more than 2 native language stations in range. A post-mortem would reveal these truths. Simple receivers would likely be well suited to markets where there were limited numbers of stations and large percentages of populations where low retail cost was paramount among consumers. Unfortunately, large percentages of those populations did not have mains power. At that time, internal conflicts in foreign nations likely to benefit from such low-cost products made it difficult or impossible to enter into contracts with foreign businesses. There were talks for India to purchase quantities of 100,000 or more before the partition of British India into India and Pakistan. Contracts were secured for the production of 25,000 two-valve radios, but the contract was canceled when the new Indian government proclaimed that henceforth all broadcast receivers were to be manufactured in-country. Talks to set up the E.C.M.E machines in-country went nowhere quickly. It is thought that Sargrove had secured a contract for 20,000 of the same radios from the Chinese nationalist government in 1946, but the civil war between the nationalists led by Chiang Kai-shek and the communists led by Mao Zedong ended that contractual arrangement. Potential markets in Africa were simply too poor to afford even cheap goods manufactured in the United Kingdom. As a footnote, in the early 1950s, the cabinet got a second life when it was used to house the Eltronic Midtronic, using 5 miniature valves on a hand-wired chassis. A brilliant engineering concept far ahead of its time, but the level of automation was unprecedented for use in the radio industry, and at the time of startup, there were considerable machine reliability problems to work out. In those years, the local power grid did not regulate line voltage nearly as well as needed for the E.C.M.E, and even short line voltage drops would force the line to be shut down and take considerable time to restart. Having on-site power backups would have helped, but remember that this project was backed by private capital at a time when the UK was just starting to rebuild from the ravages of war. It is remarkable that they could even acquire the equipment and supplies they did. With the ending of the war, there were vast numbers of able-bodied workers needing new jobs, and the powerful trade unions of the day were in no mood to see a new manufacturing process with the potential to literally decimate the manpower required to turn out radio products. And there was no apparent government buy-in for promotion of a manufacturing scheme that would likely only target export to developing world markets. The Sargrove corporate entity for radio manufacturing went into receivership, and the machinery was acquired by Pi Electronics, but there was never an attempt to revive the production method. Minimum production runs of 20,000 simple receivers could simply not be secured. Retooling for new board variations were too expensive to be considered for the many small production runs of 2,000 to 5,000 units typical for companies serving niche markets of the day. By the early 1950s, talk was common in engineering circles that the printed circuit board would soon become practical for small radios. If the printed circuit could be made economically, then revisions could be quickly implemented at lower cost than machining new Bakelite molding dies. Auto insertion tooling was too complex for all but the most simple designs. Transistorized computer control would be key to high-volume, low-cost production. That technology would not be ready for another 10 years. British industry innovation in many sectors lost its edge in the post-war years. An innovative concept for simple receivers to be used in developing countries with limited broadcasting networks and a large populace with limited disposable income. At the time, I dare say that John Sargrove was probably the only person that could have engineered and directed the building of such an amazing electronic circuit manufacturing equipment without the full backing of an industrial giant of the day. Some historians have commented that John Sargrove's accomplishments, although not fully realized, could justly honor him as the father of industrial electronic automation.